So, what time do you start to tell me that what time is missing?
10 minutes before, 10 minutes before the 40 minutes, if you wish.
Yes, yes.
Yeah.
Okay.
So 10 minutes before the 40 minutes, 5 minutes, 1 minute, and with the 1 minute you basically have still 6 minutes if you want. Yeah.
Okay.
As you wish. Just like then finish your talk and then we do Q&A.
Very good. Very, very good.
But, oh no, I'm sorry, we need, 40 minutes. So this will be like the
Okay, that works.
last 5 minutes are for changing rooms. So. Okay.
Thank you.
Yes.
Can we, Alex, can we check the mic too? I'm going to use this one, right?
This one's working?
Yeah, I think so. So, yes.
Fine.
Fine, thank you.
Can you close the doors, please?
Thank you.
Yeah, good morning. So I'm happy to introduce the next speaker to you, Valerio Maggio. He's with FBK, and please give a big welcome to Valerio.
Okay. So that works. Okay, so good morning everyone, and thank you very much for coming. Talk today's data formats for data science. Very quick slide about me. I'm a postdoc researcher in FBK, currently in the complex data analytics unit. I'm interested in machine learning, text data processing, and recently with deep divergences, with deep learning and stuff like that. I'm a fellow Pythonista since 2006, and I'm one of the main organizer of the PyData Italy that I ask you, everyone interested here, to check out. We have a Twitter account, and we had a couple of conferences in the last 2 years. One this year in Florence, and together with PyCon Italia. It was fun. We had a lot of fun, so please check out if you're interested. Another thing that's worthwhile mentioning, in Erlangen there will be EuroSci-Pi this year. It will be at the end of August, and actually the early bird tickets is gonna end today actually, but it's definitely worthwhile. So since you're in the PyData here, I think it's definitely a great conference, and you should definitely think to come. And I think basically, that's it. So thank you. No. Actually joking, So back to the serious part of the talk. Data formats for data science. the main goal of my talk is try to point to some very interesting libraries to process data in Python according to different formats they may have. And moreover, let's try to see what should be or could be the most Pythonic way to do that. Data formats came into play in the data processing step, of course. So in that case, the question is, what's the better way to process data? And since we're here Pythonistas, the better question should be, what's the most Pythonic way to do that? And we're going to see some examples of that. Data formats should also be involved in data sharing. For instance, what's the best way to share our data? And that's basically the second part of the processing. So it's for the presentation of data, so data visualization. And for instance, one possible way to answer that is try to share interactive charts for data visualization. Unfortunately, we're not going into this, but I strongly suggest you to follow the next talk about Bokeh, which is a very great library for that. And by the way, the very most common to date format to share data and indeed data plus code plus documentation is the Jupyter Notebook. I'm quite sure that any of you here already know what Jupyter Notebook is, but in case you don't, please check out this very great project. So, back to the data processing. The very first example of data format we're going to see here is the textual data format, because it's the most common data format we're going to work with in our data processing step. And let's consider a textual file basically containing numbers. So it's a huge sequence of numbers. And let's see what's the best way to process that type of format in Python. Of course, the very simple, the most trivial solution for that is open the file and read the file line by line, put the content in a list, and that's it. Probably a more Pythonic solution should be using context managers rather than opening and closing files. That's more Pythonic, of course. And basically, we have what we need. We store all the information in the files. Of course, this is not so efficient because we have to deal with numbers, and Python lists are not very good at it. So probably a better way to do that is using NumPy, of course. NumPy to the rescue. And NumPy provides, out of the box, a very useful function for that. So in case you have a textual file containing numbers that are basically matrices or multidimensional arrays, you may leverage on the load_txt function. In basically one line, you got what you need without being worried or concerned about the possible formats problem you may have in your file. And as output, of course, NumPy load_txt returns a NumPy array rather than a Python list, which is, of course, more efficient in processing numbers. If we take a look at the load_txt function here, we see in the documentation we have many parameters here. We may specify the type of numbers we want in output, in case there are comments, in case we want to convert specific columns, or we want to specify a number of dimensions for the file. That's very simple to use. There is another function in the NumPy package, NumPy library, which is gen from txt, and it's does basically the same, with the very difference that that function is able to load data from a textual file, also in case you have missing values in it. So the load_txt expects you to have a full matrix, so the number of rows and columns should match. In case of gen from txt, you have a way to specify a strategy to deal with missing values in the file. Another very common textual format you may come across is, of course, the CSV file. The CSV stands for comma separated value, but in general you may have values in this format using different characters, not only commas. For instance, tab characters, tabulations, or spaces, or a combination of that. In this particular case, we have a CSV file with the very first row, which is the header. Okay, so it keeps the information. That's quite the case when we process CSV file. So if we take a look at the very simple solution in Python, we have in Python, in the standard library, we have the CSV module, which is very specifically devoted to process CSV files. And in this case, we open the file, we create the reader, and that's it. So basically, we iterate over the file line by line, and that's up to us to decide how to store properly the information we process in the file. If you're more into the scientific, let's say scientific ecosystem of Python, I think that the very first solution that comes to you when you think to CSV file is using pandas, of course, because pandas is very great at that. Pandas builds with the read CSV file. That's very simple. Again, just one line of code. You put the path of the file, and that's it. So in output you have a pandas data frame ready, packed, and ready to use for data processing. If we take a look again at the documentation of read CSV, we see that we have many options, because actually when you process CSV file, you may come across very differences in the formats, in the handling of non-number, null values, no number values, and stuff like that. So in this particular case, the basic idea is we're not actually dealing with a file containing only numbers, but also data of different type. So the data frame is the best way to do that. And of course, as you may see in the left corner here of the slide, in pandas you may have many functions already provided to process many data formats with just one line of code. In particular, we see read CSV, Excel, or HDF, HTML, JSON, which are some other formats we're gonna see in a very few minutes. Let's have a more let's say more complicated, actually that's not so complicated example of a CSV file here. So basically the difference from the first example is that here we have the first 10 lines in the file that are basically metadata, not actual data. So the idea is we want to skip those lines when we get the data into the data frame, and that's very simple. In, of course, in pandas over there, you may see that we just need an additional parameter, which is skip rows, and we say how many rows we want to skip, and that's it. So again, pandas is the solution for this kind of thing. So to sum up a bit on the textual data format, the very first and simple example we saw. To be Pythonic, of course, use context managers. NumPy and pandas are the solutions if you're in data processing. NumPy mostly for numerical data or data containing just numbers, and pandas for CSV. Respectively, load.txt and read CSV were the functions we saw. The textual data format has some advantages, such as it is very easy to create or recreate and share, and that's very easy to process, as we saw. But of course, it's not so storage friendly, but it is highly compressible. And moreover, another drawback you may have, let's say, another disadvantage the format has is that it does not support structured information. In case we need to have some hierarchy in our data, the textual data is not the proper format to use. So we come to the second example here, to the binary data format, and we start by thinking that if we think at how much space, so how much bytes we need to represent numbers, we may see, for instance, integers and floats in native, in this example here, in native strings representation. As you can see, while the storage required for numbers in strings increase according to the number of characters we have, of course, the numbers of bytes required for numbers stored as numbers is basically constant according to the type, of course. So the idea is try to use those representation and store the data in the original format, just like binary format. So, but of course, the space is not the only concern for text, but also speed matters. When we have numbers stored as textual files, basically we lose time in converting those numbers, those texts in numbers. And basically that's it, because the conversion to int or float is not sufficient because of the underlying C function A to I or A to F. The very simple way to do that in Python to store binary data is, for instance, using the pickle module, which is included in the standard library. We have an array here. So basically we have an array of 100,000, 10,000 numbers reshaped by 10 in 10 times 1,000. And we store that in a binary file here with a pickle dump function. So we have here an array, and we may load again from the binary file using pickle load. That's very simple to use. And basically we don't need anything because it's standard library, so it's just Python. But of course, the problem in this case is that when we want to store binary data, it's not just numbers. Most of the time we need also metadata or some descriptions in the binary format we want to leverage. So in that particular case, the option is try to think to another format, and actually there is another format, which is this so-called HDF5 format, which is hierarchical data format. It is a free and open source file format, and it works very great with both big or tiny data. It's storage friendly because it allows you to have compression. That's a very nice feature. And it's also development friendly. It has a domain specific language to query the data in your structure, basically. It has support for multiple language, and that means that you may use that format regardless the person you're showing the data you have is using Python or Java or any other language. So that's a very interesting feature. And as for Python, we have many libraries. The two most famous are PyTables and H5Py. And I'm going to show you a couple of examples with both of these libraries, just to see the very difference. So if you want to create a new HDF5 file, we just need to import the module H5Py, and then we create a new file, and we create a new dataset in it. We specify the numbers of elements we want. In that case, it's 100 over there, and the type. So we have a new dataset object in output, which is, you may see here at the bottom. But when you have to deal with it, it's basically an NumPy array. So it's very developer friendly. And we may also leverage on the slicing feature here. So we may get the 10th element or slicing at step of 10. So we get basically in output an array, a NumPy array of the type we specified there. It was integer 32 bits. Actually, with this file format, the NumPy array is tightly integrated. If we're gonna use the other library I mentioned, PyTables, actually PyTables provides you out of the box a series of built-in data structures for your HDF5 files, and those are array, C array, E array, VL array, that stands for variable length array, or table. The syntax is quite the same. In that particular case here, we're creating, at the bottom of the slide, we're creating a new array, numpy array here, and then we're creating a new table, and then we're filling this table and accessing it through documentation, so it's very useful. And we append the nights here, which is the numpy array we created before. And we specify this as an array of records with those types over there. So it's integer as the first field and strings with 10 characters at most for the second field. That's very useful and very easy to use. The other important feature of the HDF5 file is that we may have hierarchy and groups. So we may structure the information in our file. So basically we start from the root here, and then we may create groups and create data sets and append those data sets to the group we created. So basically here we have a specific path to follow when we want to access the data in the structure file we created in the HDF5. Moreover, we may also create, starting from the file, we may also create a new dataset directly specifying the path, and then we may access those dataset using directly the path rather than passing by the group we created. So it's very easy to use. And finally, the last feature I want to show you is that regards data chunking, which is very useful in case you want to do in-core rather than out-of-core analytics. The basic idea is when you have contiguous data sets, basically the storage here is contiguous, but when you have chunks, you specify that to the HDF5 file that you want to have sparse data, so you want to process by chunks, and that's very useful in case you want to leverage those data processing in parallel. That's a feature supported actually by HDF5. In fact, if you wanted to show an example here, MPI is, with the MPI 4Pi library, is out-of-box integrated in the H5Pi library here. So in this particular case here in the code, we are modifying the file by multiple processes, and we are adding to the dataset, to the rank index, which is an array of 4 times 1000 numbers of integers. We're basically modifying the dataset with these array, and we're accessing, every process access each specific slice of the dataset in parallel. That's very nice. If you want to learn more about HDF5, I highly recommend this book, and also we're going to have another talk about HDF5 more into details, and that's going to be on Friday, I guess. Yes, it's going to be very interesting. Another binary format I want to show you is one I came across very recently, and it's the so-called root data format. I don't know how many of you here already know about root, but yeah, thank you very much. Actually, root is a framework, a tool, and also a data format. That's why I decided to include it here. And it's most of the time it uses for data processing in general, but it's mostly used in physics, and especially in case you are in particle physics. That's quite the case. You use root for data analysis. It's a great tool actually. It's written in C++ natively, but it has an extension in Python which is sometimes referred as PyRoot. And by the way, root 6, which is the latest version of root, ships with the Jupyter kernel, so actually you may leverage Jupyter. You may leverage the root functionalities inside the Jupyter notebook. It defines, as I said, a new binary format, which is the .root, and the basic idea is it is based on serialization of C++ objects. So that's at a glance what root is. You may leverage over here. You may say root ships with an interactive shell, just like the Python one. So it's very useful. And you may sometimes write in a sort of C++ code in these interactive shells. So you basically have a sort of interactive C++. That's interesting from some point of view. And that's the browser. So that's the file. So here you may see a very long list of leaves in this particular file, and every time you open a leaf, which should be a data container, you see an histogram here, because most of the time when you open root files you have histograms on your data just to know the distribution. But in case you want to go more into details and you want to extract the data from the root files, it turns up that you have to write these long and boring C++ code actually to perform very common operations. So basically you have to access a tree and the leaf. So the idea is that a root file, rather than talking about data sets and groups just like HDF5, it talks about trees and leaves. That's the idea. So branches and leaves. But the general idea is just the same. That's why I decided to show you. And the other reason is that we basically here accessing a tree here, and then we're that's a very weird syntax I want to show you. Actually, this is a 2D histogram. We're getting the data from the tree. We're getting these expression here. That's basically these values with respect to these other values, and we're basically forwarding the output of these row to these C++ object, which is H, which is an anonymous C++ histogram. And we iterate over the entries and the beans of these histogram to get the content, and that's it. So we have to, originally we should write these very awkward C++ code to do that, to extract data from these format. Fortunately, we have the pyroot as already mentioned, and that's the general syntax to do that in Python. But as you can see, the style, the programming style lacks of any Pythonic feature. It's very C++ style, okay? So basically you have no naming conventions, just like the ones we are get used in the PEP8. We're just basically, it seems like we're basically writing C++ code. But fortunately, there are a couple of projects I want you to show and to point you out that are those named RootPy and RootNumPy. I'm going to show you a couple of examples. They're very nice projects and very easy to use. So, getting these examples here using the pyroot, you may leverage on RootPy, and we end up writing a more Pythonic code. First of all, let's see that in case of using the get function here over the T file to get the tree name we want, we basically here, that was in the Monte Carlo in that case, we may access the tree directly using the dot notation, just like a Python object. It's very nice. And moreover, another very weird thing root has, when you're going to define a 2D histogram, basically you have to define the y-axis with respect to the x-axis, which is sort of counterintuitive. So they fixed that in the RootPy project. So here you basically specify what's most intuitively expected. So x-axis with respect to the y-axis. And you basically avoid those weird syntax of, let's say, moving the output here to this weird anonymous object by just passing an attribute here. So you said, okay, I want this row to be stored in this H2, this 2D histogram here, which I define here of type F, which means floating point numbers instead of th2f originally defined in root. Another example using the RootNumPy, which is very useful. So you want to get the data and avoid to process those files bin per bin in each histogram. So you just want, I want this histogram, I want these three, and I want the value in it, all the values in it, I want in output as an NumPy array. So that's the goal of the aim of the root to array function here. So we pass the file, the name of the tree, and then the branch we want, and then we get in output a NumPy array. And the funny thing is that actually this library is tightly integrated in the PyRoot ecosystem. In fact, we get these a NumPy array. Basically, we are here creating an histogram using the original PyRoot library here. And then we're filling these objects using the root NumPy function here, and then we draw again the histogram using the original object. That's very nice to use. So basically you're going to use the two libraries at the same time without worrying about the details because it's up to the libraries. And finally, another interesting feature about that, RootPy ships with these root to HDF5 command and utility that allows you to switch from the binary root format to the HDF5 format. Okay, that's it for the binary files. We're gonna see, yeah, thank you. We're gonna see another, I'm gonna go very quickly about this format because it's very common, and I want to talk about this format more from a data processing point of view rather than the very specific reasons why, for instance, so far in web processing, JSON is the format of choice when you have to deal with API rather than XML. And the reasons are manifold. One of these is that it's less verbose, of course, and from the Python point of view, it's more easy to process since we're basically having to deal with dictionaries and Python lists. In case you were wondering in our context where JSON is using, basically JSON is the format under the hood of the IPython notebook. So basically a Python notebook is a JSON file. But for this talk, I want to talk about JSON because JSON is the format of choice for document-oriented DBs. So the so-called NoSQL DBs. And I want to show you a couple of slides that of a test I made comparing the performances of HDF5 files versus the MongoDB, NoSQL DB. So here we are seeing that we basically had 100,000 of documents here, and those documents were structured. I mean, they were textual documents. So the basic idea was trying to build the sort of information retrieval index. So I want to store for each document all the terms and the frequencies of the terms appearing in all the documents. And more specifically, I wanted to store the particular zone of the text where all the terms were gathered. So it's a sort of structured index I wanted to build. So since these idea of structures, I just tried to decide to test if HDF5 could be a possible solution. And what I got was that from a processing point of view, the HDF file format is not so appropriate because it takes more and more time rather than MongoDB implemented in two different versions actually. So it was the flat storage rather than the compact storage. The differences were in how I structured the JSON objects going through the queries in the MongoDB, storing or not, respectively, the zone information explicitly in a nested object rather than encoded in the terms. But basically the performances were just the same. It was just a matter of how the easiest way to deal with it, programmatically, I mean. But if we look at the storage performances, HDF5 with these very simple and already provided out of the box BLOSK filter, which is a compression algorithm you may leverage, it's definitely the solution to go for. So in case you want, you have storage constraints, HDF5 is a great tool. Of course, it's not comparable in terms of efficiency in case you have MongoDB, at least in this very tight case study, and it's just, of course, there are many things we may optimize. That's not the case of this example, of course. For instance, the possibility to have data distributed on multiple clusters and stuff like that. Okay. Another format of interest for me for this talk was the HDFS. The HDFS is data format for big table. I'm going to show you a couple of slides taken from this notebook here by Mark Rocklin. It's very interesting to finally notice that there is a library which is called HDFS3 in the Python ecosystem. HDFS, of course, stands for Hadoop file system, is the distributed version of the file system built on top of Hadoop. And the data can be organized in shards and distributed among several machines. And basically, it's the de facto standards for big data. In Python, we have this very great library, which is HDFS3. It works very good on Linux machines. I had some issues to make it working on my OS X machine, but on Linux it works very good. And it has a native implementation of HDFS in C++, so there is no Java along the way. Yeah, very nice. That's the point. So the example is, let's try to see how we may leverage the analysis of CSV files distributed among the clusters. So here we create a new file system here, over there, sorry. We create a new file system, HDFS, sorry, and we ls this file system. We see all the CSV file we have here. We may read just one file here, taken from the file system, and using the read CSV file here, and put the data in the data frame. In fact, that's it. But more interestingly, we may read the CSV, all the CSV file here with a wildcard here. So basically, we're opening all the CSV files matching this query, and we're accessing here the data using this executor here, which is the server that allows you to have the distributed computation. And the very funny thing is that basically if you execute these in the notebook, the interactivity of the notebook is still available. So basically it's not blocking. That's very nice. When the computation ends, basically you have the data you have in the data format, just like a pandas data frame. So that's very easy to use and very nice. Definitely worthwhile looking at when you have to deal with HDFS. And finally, yes, we may also operate on data frame here to filter the data we have, and then we go, so we get another data frame here, and we also further processing our data. That's very nice. Since we're dealing with big data here, another mention I would make is, is about columnar database. Basically, that's the direction in which the big data world is shifting to date. We're moving from the so-called row-based databases, the relational databases, to the columnar ones. So far, there are two families, two categories, two kinds of columnar database. The Group A approach, which is the Google Table, HBase, or Cassandra, which is a sort of data model which is based on multi-dimensional mapping, rather than the Group B, which is the one chosen from these other tools here, which is the relational data model. So basically the difference is that you have data organized in columns rather than in rows, and that's very useful when you have to deal with analytics, because most of the time you end up analyzing data going through columns rather than rows. And that's very efficient, and the tool I want to show you is this one. It is called MonetDB, and the reason why I'm showing you this is that it basically ships with a built-in Python support. So basically you have, indeed, you have Python plus R built-in support in it. So you may write inside the database Python or R code for your analytics. In fact, the MonetDB type are directly mapped to NumPy arrays. So when you have to process columns in your DB, they're out of the box transformed in NumPy arrays. So you leverage the NumPy processing in it. That's very nice to use. For instance, here, we're executing a query here that returns a table. That's a function directly included inside the DB. So that's working in the DB process. We're creating a new table here that has just one column of float, and the language of choice is Python, of course, and we basically creating a random array of NumPy values, and we're returning the values, and that's it. So basically we have an output on MonetDB table. To make it working and to see it working in a more concrete example, let's say here we have two functions here in MonetDB, and here we're basically leveraging all the functions of scikit-learn here. So we're basically writing Python code in it. Here we have the confusion matrix for some processing, and then we have more details, so more statistics on the confusion matrix. We're creating a new table with all the information we want to plot here. We have accuracy, precision, sensitivity, specificity, and F1. We are storing all this information in a very Pythonic way here because it's Python here, working in the DB, and that's it. So we return the value here, and the way we use it is just included in a query. So it's a simple SQL query here. So we select the value from the two table in a nested query, and we pass the value, gathering the data from another query, and that's very easy to use. Of course, it's a very quick example. I highly suggest you to check out the dstock from which these couple of slides have been gathered in database analytics with Python MonetDB. Yeah, thank you. Okay, so that's basically the end. So a couple of things before closing I want to show is that a couple of things we mixed along the way, basically. It's more tools rather than format, actually. And I want to point you to a couple of tools very interesting and very easy to use that now belongs to the PyData ecosystem. Those tools are the X-Array and the Blaze tool. Blaze is fantastic, and it's basically a sort of one tool for all the formats. So basically, I'm going to show you a couple of examples in the next slide. And the X-Array is a sort of extension. You can think of it as an intermediate way from the NumPy structure and the pandas data frame, because the X-Array is basically a labeled ND array. So the idea is I want to have a multi-dimensional ND array, NumPy array, but I want to describe the value and the columns and the rows I have in it. So I want to access the rows or the columns by name rather than just by index. So that's the labeled array, and it's a library based on the so-called netCDF format. It's very quite popular format in case you are in physics, and it's just based on a common data model that's called common data model that basically allows you to integrate HDF file, HDFS, or other formats in one single data format, and that's very useful. Okay, so Blaze, some guys in the ecosystem consider Blaze a sort of extension of NumPy, sort of, I guess, because it allows you to out-of-core processing, which is basically one of the limitations you have when you have to deal with NumPy. In these couple of examples taken from the documentation here, you may create the data object here from Blaze, which is basically talking to a database here rather than a pandas data frame, and that's basically the same for you. Yes, the same for you when you're dealing with the code. In case for the X array here, you may create a data array gathering data from pandas data frame rather than a NumPy array here. And basically you operate over the data just like an NumPy array. So I think that's it. So just in conclusion, I would say complicated data require complicated format. Complicated formats require very good tools, but fortunately we have Python and all the PyData ecosystem for that to tackle all these problems. So thank you very much for your attention.
Yeah, thank you very much, Valerio. Unfortunately, we don't have any time for questions. Next session's coming up, but I'm sure Valerio will be happy to answer outside.
Thank you very much. I can't be on time. I can't be.
I told you,
Yeah, I know that.
But it was better than Elmer's again.
Yeah, definitely. Yeah.
Mi spiace staccarmelo al volo perché corro in bagno.
Ah, no. Ti ho fatto il plug a poco e tu non c'eri.
Comunque vero, devo gestire i problemi.
Vai. Ah, questo non va bene.
Tranquillo, c'è batteria.
Ah, ok, quindi vuoi solo questo? Yeah. No, io sono italianissimo.
Oh my god.
That's fine. So we
Ma anche no.
so
Negli anni. Negli anni. Ti è piaciuto? Grazie. Grazie.
Una cosa molto importante che quando scegliamo
10 minutes says you have 10 minutes
formato specifico
left for whatever, and 5 minutes for whatever.
Questo è interessante.
database.
In realtà io mi aspettavo una domanda del genere e la risposta a questo è dipende dal use case.
Esatto.
Non c'è una soluzione per tutto. Per esempio se devi fare analytics e c'hai i dati nel DB, io ti dico così ora senza pensarci vai su MonetDB o comunque no, MonetDB oppure altre soluzioni tipo MonetDB, database colonnari comunque. Questo è il mio, però la risposta alla domanda è dipende.
Grazie mille.
Okay, please take a seat. But don't worry, the speaker is in the bathroom, so take your time. Yes, please welcome.
That's mine.
Very much you're talking about bokeh. Okay, everybody take a seat. The speaker is approaching. So I'm really happy to introduce Fabio. Fabio is with Anaconda Analytics, and he's also one of the organizers of this conference, and he's going to talk about, oh my God, bokeh is even better. So please give a hand to Fabio.
Displays, arrangement. Okay. Cool. So, thank you everybody for coming. A brief introduction. I'm outside of working on the conference. I work for Continuum Analytics. I'm a bokeh core developer and also just solutions architect and tech lead at Continuum. This is my Twitter handle, my email, or you can also use fabio.player@continuum.io. Continuum.io. A brief summary for this talk. So usually I try to fight the boring of me speaking with some nice images. This time I will try to do it with some nice plots. Before we start, some roadmap. I start with introductions, and then I will basically go through what's in the recent release of bokeh, and then I will have a couple of extras of the bokeh ecosystem, and briefly talk about what's next now. So first, show me some hands. I'd like to know more about yourself. Who here uses bokeh? Well, that's quite a good number. Who here never heard about bokeh? That's a good number as well. And that's good. Hopefully it will show something good for you. Who here uses JavaScript for plotting or charting stuff? Okay, and who here uses D3? Okay, sorry. So here are some quick numbers before telling more about bokeh. Basically, when I joined the project, I think those numbers were really smaller. Bokeh have grown a lot recently, and this is really cool. And we had a lot more community engagement. Bokeh is an open source project, and it will stay that. It's part of the PyData ecosystem, and it's under the GNOME focus. And so what is really amazing is to see those numbers really growing every month. We have a good amount of stars, forks. Of course, this is not, we don't have 27 downloads a month on PyP. We have 5,000. And now we also have a chat on Gitter. So I invite you to use it if you have questions or doubts or anything. Aside of that, we have the mailing list and all that stuff. So what is bokeh? Bokeh is a visualization library made for Python and with data science in mind. So trying to get rid of all the problems that a data scientist have when they try to plot their results, which is beneficial anyway for any Python user or any user, because actually bokeh is not only a Python library, We have also bindings for Scala, Lua, Julia, and R, and JavaScript. So to get more about the project, you can go to okay, so let's show this. You go to the website, and to have more information about it, it's going to be complicated. Okay, you arrive at the gallery, and most of these are made by the core developers. Those are all basically bokeh plots made with bokeh. And some of these are actually user contributions. This one actually, specifically, I'm very happy. This is full implementation made by a contributor, external contributor, and it's really cool. Look at this. It's all Python, no JavaScript written. So back to the presentation. We recently just released a Bokeh 12 version. Let me change this resolution. It's terrible. Okay. Okay, a bit better. Okay, so, and you can get more information here at the main site. We have documentation is really hard, probably as hard as writing a visualization library like this. It's really complex as a library, and trying to document everything in a proper way is hard, but we do our best, and I really invite everyone that goes to the documentation, maybe for the first time or whatever, to post issues regarding what they found hard and how we can improve. So, and basically we walk through all the main topics of Bokeh and how to get through those things. So I encourage you to do this. Here's the Bokeh 12 release post, and basically all objects you see here are Bokeh plots, and they are interactive as well, so you can actually change things here. And there are different ways of doing this and how it works, and we'll be showing this during the demo. Hopefully the Wi-Fi is not so bad. And those things are connected. A few of these are connected to a server. The sliders are just JavaScript callbacks, but let's see in a moment. Cool. So what's that? Let me try. Cool. So what are the new things? I set this talk as intermediate because to have a good understanding, you probably, it's better to have an idea of what's Bokeh and have used it. But I think it's beneficial for everyone. Just they should understand and should see the benefits, even if they never see it. Bokeh comes with a Bokeh server, which is an object, it's a Tornado server that lets you write Python and say, okay, every time my plot is updated, or the user clicks on something, or there's an event on the client side or in the server side, both sides can be synchronized. So we used to have another server, and it has changed since around October or November. This new server is extremely more performant. It's all WebSocket based. There are no more REST calls. It's based on Tornado and WebSockets, as I said. And it keeps basically all the objects and models synchronized between the server and the other side. So just to understand how a bokeh server app looks like. Let's take a look at this. In our, oh wow, those are actually bokeh server apps running on that page and being embedded. But here you can see a few examples. So for instance, this movies app is a bokeh server, and it's connecting to a data store, and I can actually change stuff. Every time I change this slider, a callback is triggered on the Python side, a pandas data frame is being filtered, and the returns are sending back to the server. As you can see, it's quite fast, and it's quite reactive, and it's based on our example, which is actually slower than this. A shiny example, sorry. Let me see, show off another example. For instance, this other one shows a histogram with showing off some of the bokeh server features. So when I select those areas, there's a Python callback that recomputes the histograms, and they are sending back to the server. I can actually select multiple areas, and I can actually also define the way those selections are triggering the Python callbacks. So it can be either every time a movement happens or in the end of the movement event. So let's see. Let me. Bokeh server now runs with the bokeh command. Basically, to run on your computer, you just need to type bokeh serve and the app, or the app script or the app tier. You define your bokeh app, and it's quite simple to just run that. It accepts a lot of commands to deal with security and filtering. So if you need to serve behind an Nginx server, or you just need to serve under some ports, or like use HTTPS connections and those kind of stuff. So this is what more or less a bokeh server app is. The code for it's more or less the same thing as a trivial bokeh standalone dynamic plot. There's a lot of code here, but basically what is needed is you need to basically import curdoc, which is the only piece for the server. You need to import to create your figure, which is the plot. Say all the things that, how do you want to make it look, add some glyphs or some elements to the plot. Here we define a Python callback, and basically we put a button and say every time someone clicks the button, call this callback, and then we add everything to the root of this curdoc, and that's it. Basically, bokeh apps could be as simple as a Python script, just a main.py file, and we write everything there. Or if we have some more complicated or complex requirements, we can have a package or a directory with one file for, well, the main file, then a YAML file for a theme, how we want to make everything look and feel, static for serving static files directly from bokeh server, a server life cycle, so you can actually define callbacks to be triggered in specific moments when the service is being spawned or like things are shutting down. And then we also have a template directory with an index file that it can replace the bokeh server main index HTML template. That used to be quite painful in the past. That's a huge improvement, actually. Well, before jumping to the bokeh command, I would like to show you a couple of examples. So let me put it here so that everybody can see. Great. to serve a bokeh app, I just go and say bokeh serve. Let's do this. This one is a bokeh server app that basically has, oh, I forgot to say. I told to show. Basically, it has a periodic callback being called every, I can't remember. But it is redoing for Fourier harmonics for the whole circle. And there's a lot going on in the back end. It's quite fluid as well. Another example that is quite nice is, let's see. Show OH. In this case, I'm serving a bokeh app that is the directory, and all I need is to give the directory name. This is an OHLC plot that is basically recomputing all the statistics and all the simulation every, I think it's 3 or 1 millisecond. And as I change the sliders, the model is changing its behavior. And as you can see, it's quite fluid. And the rate is fast enough to keep the rate and sync everything between the Python side and the JavaScript side. So it can be really anything you need. Like we are doing simulations with NumPy and optimizing with Numba, but you could connect to your data source or do whatever kind of stuff, crazy stuff you need. Cool. Let me try. Okay. Let's move ahead here. So, bokeh command. We also have two other, we just saw before, the bokeh command, serving the server. It also have different options. The most important ones are HTML. Basically, you can just, if your app doesn't have callbacks, but it's just like client-side callbacks or just some interactions with the widgets, you can use bokeh HTML. It will create an HTML file that you can actually send by email or serve anywhere, and it contains on the interactions that you need. And bokeh JSON basically saves a serialized JSON file that you can then take and use elsewhere to create bokeh plots. All the information, I try to put the related links under every slide. Okay, client-side callbacks. Basically, bokeh lets you also write JavaScript if you want. So let's say you don't want to have a server, you want to have some interactions, and like in this case, I have a notebook, and I don't need a bokeh server. I want to just have some sort of this dynamic plot, and every time I move the slider, I want this to move. Basically, I would like to write JavaScript to do that. And yeah, bokeh lets you, it provides a custom JS widget that lets you write either CoffeeScript or JavaScript and define the code. And it gives you access to the lower level data source. So in this case, this plot have one type of glyph, which is scatter. And then it's connected to one data source. You can say, okay, on this data source, slide the objects or do any computation or anything. In this case, it's just replacing the source with every year as it changed. Those JavaScript callbacks, they extend the capability. We are working, this is kind of yellowish, because we are working on basically doing canned JavaScript callbacks for the things that most people want to do. But we had a dream also to say, okay, what if we could write Python and make it work on the browser? And it's not a dream anymore. So with this new release, you can actually write Python functions that we kindly translate to JavaScript for you, and they work on the browser. So, like this case, I have a bokeh plot, a simple curve that I have sliders, and I want to tweak with the curve using the sliders. So to use Python, you just need to define your plot stuff and define a callback and define what kind of objects it need. In this case, the source, which is the data source of this plot, and a window object. The window object is actually the JavaScript. But so basically, you get the data from the source, you tweak with your parameters. You basically read the slider values. In this case, we use the JavaScript syn function to recompute the numbers. And then basically we get this object, call it as a callback, and we pass to the slider for every slider. So every slider here will be calling a JavaScript function that was written in Python. And if you don't believe me, well, I already showed you actually. This is what's happening on the first page, but like let's show it locally. Okay. I think that's one that should work. No, this is a similar thing. Slider. Maybe it's elsewhere. Maybe it's just slider. Okay. And that's that. And in the 011 release, it just supported Python 3. Yeah, but now it also supports Python 2.7 because.
So there are no network callbacks.
Sorry?
There are no callbacks to 2.7.
No, this actually is it just creates an HTML file, slider, and that's what it's serving. There's no active callbacks or anything. Like, it's standalone. Actually, you can just get that and send to a client and a customer and show like things happening. You can actually write notebooks with those kind of things and use bokeh bokeh HTML to convert this notebook to an HTML file and just send the HTML file to someone. It will convert the notebook to a bokeh HTML standalone file because it only grabs the cells that were created with bokeh.
Does it have any limitations? Some features don't work in that, or?
Anything that is notebook centric or anything, yes, anything that is notebook centric or that relies on your local data would not work. But anything that is not related to your environment should work.
So if I embed the data within the callback, then
Yeah, then you're fine. Yeah. Cool. We also now have a better support for Jupyter Notebook callbacks. So it used to be quite hard because Jupyter have their own WebSockets that connects to the Jupyter WebSockets. We have our WebSocket stuff. Right now, you can actually we release the push notebooks callback that you can actually use to do the same thing and use IPython notebooks widgets to connect to a plot and recompute stuff. Okay, another big problem in Bokeh was that honestly it didn't look so well, especially the widgets. They used to suck a lot, but they are super cool and better now. And also it used to have really a lot of limitations with laying out stuff, so it was really hard to lay out plots in the way every user wanted. So this one is a quick comparison about how things look now. Oh, where's my mouse? It's there. Okay. You can see the old one here and the new one here. There are a few tweaks and changes in this case, but the main things are that Hbox and Vbox, which we used to be the old boxes, they are gone, luckily. Now we have row columns approach. We also have a widget box which basically makes it easier to build rows and columns. And it's quite simple now to lay out stuff and lay out stuff in a way that axes are aligned and you know you can define where to put the title and legend. Actually now title and legend are can be put out of the plot itself. So Bokeh used to always need the legend inside the canvas area. You can actually now put it outside. This is an example of layout, column layout. It's fairly easy. You just need to say, okay, layout, column, and then tell what to put in the column. And same for the row. And same for grid plot. We basically use array lists to define what goes, and we compute everything. We actually have a responsive flag that you can use to make things responsive. And yeah, there are a few options like for the sizing mode, stretch or other options. Okay, some layout examples I already showed you. Custom extensions. So a lot of times Bokeh do not contain everything. Like if you want to have a slider that looks differently, or if you want to have a different kind of plot or a different kind of tool, you can actually, Bokeh now provides a mechanism to extend our models, sort of a plugin system. So you can actually create your own Bokeh model, either on the Python side only or Python and JavaScript side. You don't need to, we try to make it less complicated as possible. So if you need to make changes to the JavaScript side, you can actually define that on the Python, your new Python client class, and you define a specific new attribute. So how extending Python classes work? You basically, well, actually, let me use this to help me. So to extend Bokeh on the Python side, it's quite simple. You just inherit from the model you want to extend and add everything you need for your custom model. If you need to extend on the JavaScript side, it's a bit more complicated. You need to basically, you have two options, write your CoffeeScript or JavaScript file and then use it, or you can actually just define your implementation in the model itself. And I can show you here. And that's all that, basically. You define your Python class and you define the special under implementation attribute to define the CoffeeScript and the JavaScript. So the result of this, in this case, is, for instance, if I want a new hipster, old school range, I can just define all these things, and it works. And it injects all the JavaScript and the HTML into the page and replace the custom slider one. So, but you can also extend more things, like what if Bokeh doesn't support 3D and we want to have a 3D model? Now you can do it. And you can, so for instance, Bokeh, serve, show, surface 3D. You can actually have use whatever JavaScript library you want to integrate with Bokeh, and have the Bokeh managing the higher level things, and having your lower level JavaScript API doing the other stuff. So in this case, it's using Vue.js that consumes a Bokeh data source and plots the 3D dynamically on the page. Cool. Annotations. Bokeh now have real annotations, so you can actually use stuff to annotate your code. We have arrows, like this case, and it's not that complicated. You just import what you need. Add as a layout, so in this case an arrow with open head, and I give the coordinates. You can actually tie that to data sources. This is a box annotation here to highlight a specific area. And yeah, the way you use it is more or less the same. You have labels, like in this case, with different aspects, and we can tie to different models. Spans. We have much better geo support. Now we actually support a GeoJSON data source that you can use to drop points on the screen. We still have Google Maps support, but Google just changed their terms of using APIs, and basically you need to have your own key to use it. Basically, they didn't say anything and changed from one day to the other. All tests failed, so it was not nice. And it's an extra step for the users, and we are trying to check what we can do to make it just work. Geo support, we have good support for tile renderers. So if you have any service that is a tile renderer, we provide support for that if it to consume Mercator projections. New TypeScript and JavaScript API. So TypeScript and JavaScript APIs have it pairs down the plotting API, the models API, and a brief charts API, which is not like the Bokeh core charts API. It's just a handy thing to create like bars and pies on the JavaScript side. Like in this case, JS transforms. We have new JS transforms, which means if you have a data column, of data in the Python side, and you want to basically create new data from that, like plot objects from the same column with some transformation. We support this. We now support jitter and interpolation. So if you have just a number of dots and you want to interpolate in different ways, you just specify the kind of interpolation you want. We have now better WebGL support, and it's actually quite fast. Just show quickly an example. I'll just show quickly an example here of, and it now supports all the glyphs basically. In this case, we have WebGL not activated, and if I zoom in, you can see this time when things are gray, it's basically recomputing everything. And this is how we're computing to render everything. This is how it's rendering with WebGL. Those both examples have 10,000 points. We have examples with 1 or 2 or 300 points, and WebGL performs quite well. But now there's a whole ecosystem growing around bokeh as well. I want to mention 2 projects that are quite cool. The first one is HoloViews, and basically HoloViews let you have annotated data. It's basically notebook centric and lets you have annotated data, and it pre-builds, it creates a new grammar to let you do specific complicated stuff to your annotated data. So let's say I want to slice my big chunk of data in different layers, in different dimensions, and I want to have a slider to basically go through different steps and different layers of that cube of data. It lets you do that quite fast. Those lines create this plot here, and as you can see, it's quite nice to read and quite dense in terms of quite lean in terms of code. This other one project, I would say it's fairly cool. Basically, DataShader is part of the bokeh family, and it lets you plot massive number of data on the browser. This example here is taking the New York pickup and drop-offs data set. It's a 12 million data points data set, a few gigabytes, I think it's 10 gigabytes of data. And it basically just works. So, and it's, well, let me show you. Hopefully we still have time. Okay, I should have that somewhere. Okay, I still have questions though, right? No. Okay. So you want to have questions? You want to have questions, or you want to see this? This, cool. So very briefly, one problem with big data is that if you have points tend to overlap. So in this case, if I have 12 million points, I'm just plotting 1,000 here. You can barely see what's happening. In this case, 10,000, it's over plotting because you don't really understand anything anymore. You can tweak with the data and say, okay, let's just have 10% alpha and 10% reduce the size of the dots, but you don't understand stuff yet. Same here, you try to improve, and you can actually see that the problem is that data is not linearly distributed, so you have to, have transforms and try to build better data. But the best thing you can, this is actually changing in using a logarithm transform. This one is actually changing and using an equalized histogram. So basically, DataShader lets you specify all those transforms and have a nice set of transform operations before it gets stuff to do okay. So basically, every time you have data in a screen, you only see the points you would see. So in this case, I can zoom in. It will basically go in and out and recompute stuff if I didn't break anything. Let's reload that. Oh, this is the one on the browser. Anyway, this is being served on the network, not locally. Yeah. If I still have time, I will show you. Otherwise, just grab me later. Alex, do you have time or no? No.
3 minutes to the next call.
Okay, I think 3 minutes is maybe fine. Let's see. Thank you.
Yeah, thank you. You're happy to answer questions on the conference, aren't you?
Yeah.
Thank you.
You know whether we reset lightning talks every day or do we carry on?
We are resetting now,
Reset.
I think.
Yeah.
But we could carry on. I think it's...
I think resetting. People should get early so they
Yes,
the lightning
yes.
talks.
But it's really hard. It stops like it. After 3 minutes, it's done. Hi.
Yeah. For questions, could you please move outside? We can prepare for next speaker. Thank you.
What steps did you have to take to transform
Yeah. You can give a notebook or a
It's a bit flickery. But it was with Fabio's as well, so it's the only option we have. Would you mind if we just try this? Not to be too stressful just before the talk.
At least we have a working option.
Yeah, it's a little bit figure. It's not bad, or it's a little strange.
It didn't.
Probably it's good.
It didn't like this.
Okay. At least it's not flickering. Oh.
It really didn't like that. Okay. Now it's just gone. Here we go.
Oh, yes. Okay, so it's Rochi.
Larger if it's
No, Rochi not. Rochi, European conference, right? Rochi from the gear, you work with Go Data Driven, and you're going to talk about the risk game. Okay.
You'll show me the challenge, right?
Yes, you want Q&A?
If I have time.
Yeah,
Not
okay, we have like,
lunch afterwards.
yeah, we have lunch afterwards, so you can have 45 minutes talk, that's a luxury before the lunch talk, and I'm going to give you like a 10-minute science until the very end. So,
Okay, everybody, please take your seats. We're preparing for the next speaker. Okay, welcome everyone for our next speaker. It's Rogier. No, sorry.
Rogier.
Rogier, sorry. Rogier van der Geer. He's with Go Data Driven in Amsterdam. And if you ever played Risk, you will get some nice insights how you can actually see how to conquer the world with a simulation. Yeah. So please welcome.
Thank you. So indeed, I will tell you how to conquer the world, at least in a tabletop version. And I will tell you how you can use genetic algorithms to actually improve your risk skills. So, in other words, we'll be doing some risk analysis. An overview of this talk. First, I'll just introduce the game of Risk to you for the people that haven't played it any before or just not recently. Of course, if you want to analyze the game of Risk in Python, then you need a Risk framework to do so, to actually play the game. So I'll show you how I implemented Risk in Python. Then I'll tell you what a genetic algorithm is actually, and then we'll see how you can use a genetic algorithm to play Risk. So let's start with the game of Risk. A little history: it was invented in 1957, so it's over 50 years old, as the conquest of the world, but since 2 years later, since 1959, it's been called Risk. And according to the publishers, you can play it with anywhere between 2 and 6 players, but I'd say you should need at least 3, because for 2 the rules are different. And the playing time is anywhere between 1 and 8 hours, depending on how long you take to decide what you're going to do. I can tell you in Python this goes a little quicker. So, okay, everything revolves around this game board. What you see here is just the map of the world, divided into 6 continents, just like in reality, and 42 territories. And so these territories are divided by borders, and so they're neighboring territories if they either share a border or are connected by a red line that goes over the sea. So now, when you prepare the game board, first you divide all the territories over the players that you start with. So imagine we have 4 players, we'll divide all the 42 territories among those players. So we assign them to, well, we have red, blue, yellow, and green. And, well, first we put 1 army on each territory, and so the ones in the circles are here to show that there's 1 army on every territory. And then every player, one by one, gets to place 1 more army on 1 territory, wherever they want to put it, up until the point that they all have 30 armies on the board. So that looks like this. So after that, the game is ready to be played. And then, so each turn consists of 3 stages. First there's the reinforcement stage, then the combat stage, and then comes the fortification. So what happens during these stages? Well, first, during reinforcement, a player places some additional armies on the game board. And this really depends on his status in the game, how many armies, or how many territories does he control, and which ones. So first of all, he gets 1 army for every 3 territories he controls, plus he gets some bonus armies for owning a full continent. So for example, if you own the entire continent of Europe, you get 5 more armies. And then there's some game mechanic that I won't explain in detail that is called reinforcement cards. You can earn these by claiming another territory, and you can get a little bit of additional bonus from that. So after reinforcement, you can attack other players. So this is the combat stage. So what you can do is you can take some armies from 1 territory and then attack a neighboring territory with these armies. The battle is decided by using dice, so by chance. And basically you only have a good chance to win if you have more armies. So really it's only about having a lot of armies. And then, so if you win, if you conquer at least 1 territory during this stage, you get 1 of these reinforcement cards. And then after you've attacked, you can attack indefinitely during your turn until you've had enough or you run out of armies to attack. And then the last stage of the turn, which is a little less interesting, is fortification. This is where the player moves some armies, so he can pick 1 territory and a neighboring territory and move a few armies between those. You can only pick 1 combination of territories. They have to be neighbors, and then you can place as many armies as you have there. So that summarizes the game. Well, not really, because then there's the winning of the game. So each player gets a mission, and by completing the mission, the player wins the game. Of course, if you just eliminate all other players, then you win. But there's also the missions, like listed here. There's quite a few. I haven't listed all of them, but for example, there's missions like Conquer Africa and North America. So conquer 2 continents, destroy another player, or conquer at least a certain number of territories. So now let's move on to Risk in Python. So I've built a Risk framework in Python that consists of 5 classes. So they're listed here. First of all, the board, which handles all the armies on the game board and all the territories which connect to each other. Then there's the cards, which is handles the reinforcement cards of a single player. Then there's a mission, which describes a mission of a single player and can also check whether this mission has been achieved. Then there's the players. Of course, well, these are the actual players that need to make the game decisions on what they're going to do to win. And then in the end, there's the game that keeps track of all the other game mechanics, like the turns and all the stages in the turns. Okay, so let's have a look at the first object, the board. So when we can just import the board from the board file, and then we can create it. And when we do this, we have to specify how many players we are going to use, because it already randomly distributes the territories amongst the players. So then we can call the plot board method from the board, and it will actually show you where the territories, which territory belongs to whom, and where the armies are. Of course, this initializes only with one single army in every territory. So the board allows for very easy manipulation of the armies on the board, so you can easily just change the owner of a territory. We can also give it to an owner that's actually not yet in the game. For example, here I set the owner of territory 0, which happens to be the one right here, and set it to player ID 5, which is the black player. And then I place 15 armies on there. And then if we plot the board, we can actually see that this is the case. This is an easy way to cheat. So the board is also aware of the layout of the territory. So let's move back to this picture here. So around the territory, which has 15 black armies on it, there's 5 neighbors, of which 3 are owned by red and 2 are owned by blue. And so if we ask the board, we can ask for the neighbors of territory 0, and it will tell you that there are indeed 5 neighbors, of which 3 are owned by player 0, that's red, and 2 are owned by player 1, that's blue, and all of them have 1 armies on them. So this makes it easy to decide, for example, which armies or which territories you're going to attack from where, because you can just ask the board, which are my options. Okay, so it can also handle attack moves, so you can just call the attack method from a certain territory to another territory. Of course, this has to be a territory that's owned by someone else with a certain number of armies, and it will throw the dice for you, and then if you're lucky, like in here, you can take over another territory. So like here, the black player moved into the Middle East. Of course, that was easy with 15 armies against 1. So then there's also the missions. We can get all the missions with the mission function. Also here we have to specify the number of players, because this depends on the number of players. And here there's a list of all the missions. So each mission has a description. There's quite a few that ask you to conquer a certain set of continents. Some of them ask you to conquer 2 continents and an additional continent of choice. So then you have to just own these 2 plus an extra, whichever you choose. Or own a certain number of territories, or sometimes even have 2 armies on each territory to win. And then there's the last missions that ask you to eliminate another player. And of course this depends on the number of players. If we had 5 players, then there would have been 1 more eliminate another player mission. Okay, so we can just take a mission, and so it will give you a representation that tells you what the description of the mission is and to whom it's assigned. By default, it's not assigned, and we can assign it to a player. So for example, if we assign it to player ID 0, then it will tell you it's assigned to red. And then we can ask it whether the player has won the game already, and we can have the mission evaluate the board and check whether the player has actually won the game, which in this case isn't true. Now there's one special case. So that is when a player is assigned to kill himself. So for example, if we take the last mission here, this is eliminate the yellow player, which is so far unassigned. We can assign it to the yellow player, which is player 3, and then it will tell you, well, there's a fallback mission. It will have to conquer at least 24 territories, which is now assigned to yellow. Okay, so that all works. Then there's also the players, of course. Well, I'm not going to detail into how the player object works for now, because I made several versions. We'll encounter some of them later in the talk. But the players have to implement 4 methods, and that is one method for handling one of the game stages, so the reinforcement, the attack, the fortification, and then the turning cards for the reinforcement cards. And then, well, of course, there's the game object. Instead of just explaining what it does, let's just go through a full game. I've also implemented a random player object, which just plays the game randomly. So if you think one of the players makes a stupid decision, well, it's probably just because it's just random. So we can just import the game. We need to also provide it with a few players. So let's create a game with 4 random players, and then we can plot the game like we used to. You can also see that right now it plots some statistics that are probably not easy to read from there, but these are not so very important. So the game board has been divided up amongst the 4 players, and now the first stage is to put armies on them. We can tell the game board to initialize a single army. This asks every player to place 1 army on the board. And you can see that, so for example, here there's a blue army, and here there's an additional green army, there's a yellow army, and there's a red army here. Now, we can keep calling this function, this method, until all the players have 30 armies on the board, but of course that would be boring. So we can just say, call initialize armies, and this does that, exactly that, until we're done. So now you can see, if you're willing to count, each player has exactly 30 armies on the board. So now we're ready for the first turn of the red player. And the first thing the red player may do is place some armies on the board. So we can do that by calling the reinforce method and give it the player object that it needs to decide on what it is going to do. And then you can see, if you have a close look, that indeed there are a few more armies on the board. So let's go back to the previous situation a little, and then you can see, for example, here there are now 3 armies, and then after the reinforcement there are 4. So there are in total 3 armies have been placed on the game board. Okay, so now then comes the attack phase. It works the same, you just call the attack method, and then if you take a very close look, let's not go into all the details, but it will have actually attacked something, lost some armies, but in the end not conquered the territory. Then there's also the fortification phase, and then a few armies move on the board. Okay, so then now is blue's turn. Let's not go through blue's turn all the way. We can just say play turn, and we'll play blue's turn. Now blue did the reinforcement, the attack, and then the fortification. And we can keep doing this until the game has ended, or maybe just for 10 turns. And then you can see that, well, red is doing pretty well. Yellow has taken over South America, and green almost took over Africa. But, well, so we can keep doing this until at some point the game ends. We can also ask the game whether it has ended so far by just checking all the missions if one of them has won. And then, of course, after a certain amount of turns, in this case it's 54 turns, one player wins, and that's the red player. Well, of course, this is not a very good strategy the red player is doing right now, because he has all his armies in Australia here. But that is because, well, he's randomly moving armies, and the chance of moving his armies away from there is fairly low. But that's not the point of this. So what I've demonstrated here is that we can actually play Risk in Python. Okay, now let's move on to genetic algorithms. So what is a genetic algorithm? So it's a machine learning algorithm based on evolution and natural selection. So basically how also nature evolves. So why have I chosen a genetic algorithm? Well, it's easy to use with just having very little knowledge of a problem, and it's very robust against noise and many dimensions, and that will come in very, very handy. Okay, now let's have a look at an example. So imagine we're trying to solve this puzzle, and the solution of a puzzle is a string of 16 bits, and here I'll show the solution. So for example, it's this string of 16 bits here. And now imagine we don't know the answer to the puzzle, but the only thing we can do is provide it with a possible solution, and then there's a function that will tell us how many of the bits are correct. So for example, if we try this string, it would yield 7, because the first 4 are all correct, the second block is all wrong, the third block there's 2 correct, and in the last block there's only 1. So that would yield a total of 7. Now, of course, this is a problem that's simple enough to just brute force. We could easily do that. But let's do it the genetic way. So what we can do, we can just start with generating a few random solutions. So, for example, take these 4. We can evaluate all of these, and then we come up with the score of each solution, which in the first case, the top and so the first one and the second one have a score of 9, and the second and the third and the last have a much worse score. So if we just look at these solutions, let's only have a look at the best ones, because we're not interested in bad solutions, right? So we take those top 2 solutions, and then what we can do is we can split them up. We take these solutions, we call them parents, and I've colored them right here. So there's a red one and a blue one, and we can split them up and paste them together to form children. So if we do this, if we take the first 8 bits from the blue solution and take the last 8 bits from the red solution, we end up with a far worse solution than we've had before. So score 9 drops to score 6. But if we do it the right way around, we take the first 8 bits of the red one and the last 8 bits of the blue one, we find a solution that has a score of 12. Now there's another way to improve a solution a little bit, and that is by just randomly mutating a single bit. So for example, we take the solution we just found with 12, with a score of 12, and we can just randomly mutate bits. So for example, take the second bit and change it from a 1 to a 0, and then we'll see that the score drops to 11. But sometimes we're lucky and we'll find a solution that's a little better than the solution we had before. Now we can keep doing this. Take 2 good solutions, combine them, and hopefully find better solutions, then mutate them a little and combine them some more. Keep doing this until we have found a satisfactory solution. In this case, we know that the optimal solution will have a score of 16, but in many cases we don't actually know how good the optimal solution will be. So, in short, a genetic algorithm requires you to have a random, or maybe not random, initial pool of solutions. You need some evaluation function, you need a combine method, and a mutate method. And then you can just keep doing that and see your solutions improve. So, now let's think about how we would implement a genetic algorithm for risk. Well, there's one problem. So when we're going to evaluate a risk player, we don't have a function to evaluate a score like this. So when we take these strings of bits, we can easily evaluate them and get a score that tells us 9, 6, or maybe 12. But if we have 4 risk players, let's say player 1 through player 4, which one is the best? There is no function that tells us how good it is. So we could, of course, have them play a game. So let's play a game between the 4 players, and then player 3 wins. Is player 3 the best then? Well, we don't know, because of course if we play them more games, well, there's an element of luck here. So it could be that actually some other player is better. So we can have them play like 6 more games, and then we see that player 1 is actually won the most games. So is player 1 the best then? Well, likely. We can play hundreds of games until we're satisfied with the precision we've achieved. But of course this takes time. But now what if we have 8 players? We cannot have 8 players play a single game, because the game only goes up to 6 players. So of course we could have them play 2 games. First, player 1 through player 4, they play a game, player 1 wins. Then player 5 through player 8 play a game, and player 7 wins. But does this now mean that player 1 is better than player 5? Well, it could be, but we don't know. We don't really have a way to know, unless actually the players from the first pool played against the players from the second pool. So the best solution would be to play games with all combinations of players, which in this case would be about 70. But remember, one game in every combination is not enough, so we end up playing a couple thousands of games. And this is only for 8 players. Now imagine we have 100 players. Then already playing a single game for every combination would require millions and millions of games. This is not a solution, so we cannot do this. So that's why I've decided to use TrueSkill. So TrueSkill is a Bayesian ranking algorithm developed by Microsoft Research, and they use this to rank players of Xbox games. It's very interesting. Let me give you an example. So imagine we have 2 players, and they have never played a game. Then how well are they? We don't know. We don't know their skill. So if we just plot our belief of the skill of these players on the axis. So here on the x-axis we see the skill of the player, where in the right would be very good and in the left would be very bad. We don't know how good the players are, so there's going to be some distribution. They're likely not extremely good, likely not extremely bad, but just somewhere in the middle. That's all we know. The distribution is fairly broad. By the way, I took these plots from my colleague Vincent's blog. If you want to play around with these distributions, go there. So now, so before these players, they had never played a game, so we didn't know anything. But what if they do play a game against each other, and then player 1 wins? Well then, of course, we're still not sure how good they are, but at least we think that it's likely that player 1 is a little better than player 2. Now, if, on the other hand, player 2 wins, then it's likely that player 2 is a little better than player 1. So this is very nice. This is exactly what we expect. But another very nice property of this algorithm is that imagine that we have one very good player. So the top player here, player 1, is very good. We already know it's played many games, and we know it's very good. So our belief of the skill of this player is all the way on the right side of the plot. And now imagine that player 2 is new, so we don't know anything about it. And then, so it's just a broad distribution somewhere in the middle, like before. Now imagine they play a game against each other, and player 1 wins. Well, we expected that, right? Player 1 is a very good player, player 2 probably wasn't too good, most likely. So nothing much changes. Player 1 just got a little better because he won another game, and player 2, well, nothing much happened. But on the other hand, if the new player, player 2, wins the game against player 1, then suddenly we realize, hey, he must be very good. So you can see that the distribution of our belief then goes all the way to the right. And now this means that in order to have an idea of the skill of a player, or the skill of a risk bot, you don't need all players to play against each other. You can just use use TrueSkill to get an idea of the skill of the player and estimate the belief. Well, you could implement this in Python, but of course, you know, like for most things in Python, there is already a package. You can just install it, and well, you can just use it like this. So by default, every player gets a score of 25. We can just make 2 ratings, A and B, and then you see, so each player has a score, a mu of 25, and the sigma, which is the width of the distribution, of 8. So that's very nice. And then after a game, we can calculate new ratings. So for example, if we before have, so we have A and B, each with a rating of 25, and then we have them play a game where with 2 groups, so we have player A and player B, each in a group, and so the first group won, came in first, and the second group lost, came in second. Then we can see that actually, so the mu of player A increases to 29, and the mu of player B decreases to, sorry, it breaks off here, to 20. On the other hand, if, and then after this, if then A wins again, you can see that the score hardly increases anymore, because, well, we already knew that A was better than B. On the other hand, if then B wins after this, the scores go back to fairly close to 25 again, because, well, they've both won a game. So this is very nice. Another very nice thing about TrueSkill is that I can also handle larger groups and multiple players in a tie. So for example, if so we have a risk game that there's only one winner, then we can say, well, player A won the game, and B, C, and D all lost the game. Cool. So now we can use that to rank our players and evaluate them. Now all we need to do is implement a genetic risk player. As I said before, the player needs to be able to reinforce, attack, fortify, and turn in his cards. So how would I do this? How do I pick a move? Well, the easiest way to do this is just create a list of all possible moves I could do. So for example, when reinforcing, I have to place an army, then I just make a list of all possible territories I could place the army. And then I rank all these moves based on some criteria. And then I just pick the top ranked move. So what kind of criteria would I use? For example, if I'm placing a reinforcement, let's define some metric called the territory ratio, which is the number of hostile neighbors around the territory divided by the total number of neighbors around this territory. So this gives me a measure of how far this territory is into enemy lands. And of course we can have some metric of how important is this territory for my mission. Of course, if I have to conquer Africa and the territory is in Africa, then I need this territory for my mission. And I can define multiple more of these. But let's take these two as an example. So imagine now I have 6 territories and I need to place an army on one of them. I can calculate this territory ratio for all of these, and I can also figure out whether the mission is applicable to all of these territories. And imagine I own these 6 territories, they all have an index, and so for territory 10 has a territory ratio of 0, which means that it has no hostile neighbors. Well, so probably you don't want to put your reinforcement army there, right? Now, how do we rate, or how do we create a rank of these territories using these numbers? Well, we can just define a reinforcement rank, which is then the territory ratio times some weight plus a mission times some weight. And let's say that the territory ratio weight is 1 and the mission weight is 2, and we can calculate this rank like this. So for example then for the first territory, territory 10, the territory ratio is 0, so times 1 that's still 0, plus 1 times 2, that's 2. We can do this for all territories, and then the top ranked one is territory 18, so we place our army there. But now how do we figure out which weights we should use for this algorithm? Well, for this we go the genetic way. So what we do is we initialize all the players, lots of players with random weights. We play many games, we drop the bad players, we combine and mutate the good players to create new, maybe even better players, and repeat this until we're done. So how does it look? So for example, I take the territory ratio weight and I just randomly distribute, I take a random distribution between here minus 25 and plus 25. Why this interval? Well, I don't know, I just picked something. And then we play lots of games and we drop all the bad players and we create new players by combining and mutating these weights. And then you can already see that, so this was the initial phase. After one iteration of the genetic algorithm, we already see that the players with a higher territory ratio weight are definitely better than those with a lower territory ratio weight. This is after one iteration. Of course, one iteration is not much. After 10 iterations, all the players with a negative territory ratio weight are almost gone. And after 40 iterations, you see this is a nicely centered peak around 15. So why 15? So what is this 15 normalized to? Well, I did a little trick there. And so for one of the weights, I fixed it such that it could never be larger than 1. In fact, I allowed it to be either -1, 0, or +1. And you can see also this, well, this one moved a little slower, but you can see that this, after 40 iterations, has a nice peak at 1. So this means If you're going to decide where to put your reinforcement, looking at the number of hostile armies near your territory is 15 times more important than whether or not the territory is relevant for your mission. So I've implemented 5 factors for reinforcement. So this would be whether or not do I get bonus, so continent bonus armies for completing a continent, or for owning a full continent. So either the direct bonus is then, if I do already own the continent, the indirect bonus is also applied for not having a full continent. Then there's the mission, then there's the territory vantage, which is the territory ratio I just explained, and you can do the same with armies. So I can show you more plots. So actually, so the army vantage ratio weight goes negative. You can see here at iteration 40, it's a nice peak, a negative peak. So this means that you should never place reinforcements next to very large armies that are close to your borders, which also makes sense. You can do the same for direct bonus, and or for just all the weights I've used for all the player functions. So this is the result after running 40 iterations. Of course I could have run more, but this already took me 80 hours of compute time, so I decided to stop. So this is the result. If you want to be a very good Risk player, study this. I, by the way, do not claim to be a very good Risk player. So are we done now? Well, no, definitely not. I mean, look at this. There's lots of these distributions have not converged to a single peak. Well, maybe they are. It doesn't really matter so much. But in the end, we do expect this to converge at least a little more. So we could spend a little more computing time on this. But then, in the end, by using these weights, we only allow linear combinations. Maybe it's much better to use like the territory ratio squared plus the mission times something. I don't know. We could implement that, but that would create an even larger dimensionality and would even take more time to run. And then also, of course, well, these players do not look ahead. They don't plan. They don't. And they definitely do not adapt to opponents' plans. So, of course, these are definitely not the most advanced Risk players you can make. But I thought it would be a nice exercise. So, yeah, I'm early, sorry. In conclusion, by now we can play Risk in Python. I've made a genetic representation of a Risk player, and I've used a genetic algorithm to find better Risk players. I'm planning to make all the open source, all the code I've used for this. I just need a little time to clean this up. Watch our blog. I'll publish the link to the repository there once I'm done. And until then, any questions?
Yes, questions. I have a question myself. Were you able to identify like a superior strategy?
No. So I had a look.
Please do come back next year. All right. Yeah.
Thank you very much for everything. I would prefer if you would use the politically correct term of liberating the world. And the other thing is, which precaution did you take to make sure not to develop Skynet?
I'm sorry?
Which precaution did you take to make sure not to develop Skynet?
Well, if you, with Skynet, you can conquer the world, that's good enough, right? That might be the best strategy.
More questions?
Thanks for the talk. I really like Risk. So your best player, is he good? I mean, have you tried to play against your best player?
I have, but well, so the interface for playing the game yourself is a little cumbersome. You have to actually call the method. So I played a single game. It took me an hour or so. I lost. But of course, this isn't really good statistics to tell whether or not these players are actually better than any human player. I guess that would take too much time to actually figure out.
You must have. Oh, yeah. Sure.
What's the worst tactic that you've seen?
Yeah, so actually at the beginning, I had really trouble running the first iteration of the genetic algorithm. Turns out, depending on your weights, some of the players do not attack at all. And so if you have 4 of these players in a single game, then you have no attacks at all in your game, which turns out to be a fairly poor strategy.
Hey. Yes, here.
Okay. Hi. How much trouble was it to visualize the data with the map and the numbers? So how much time did you have to spend on that?
That was actually one of the easiest things. It's just, well, taking a figure and then placing these dots and numbers on them. It took me half an hour, I think.
A little bit more of a general question, because when you're designing something like this, you take the object-oriented approach. Sort of what's the best advice you can give to people if you're starting out with a problem like this? Like, how do you decide how to call what object and where to put what layer of abstraction and sort of keep it all organized when you're designing this for the first time?
The best advice I can give you is just think about it before you start implementing. So if you implemented, so I started with an implementation of the game, which then in the end didn't allow any player to interact with it. That's not so useful. Just think about it before you do it and make logical choices of what you represent in an object and what you don't. Thinking about it, I don't think there's a general rule, what is the best solution. Just think about it before you do it.
Okay, so thanks for the talk. I have just a question about the, how is it called, true scale metric. It seems to me that it's kind of similar to the error rating, so, but just instead of a single number, you just use a distribution to express the player's relative skill. So is this it, or is there anything more to it?
I'm actually not aware of the other method you named. What was it exactly? Okay, I don't know it, so it could be the same. I know that Microsoft patented this one, so there must be something different at least, but it could be very similar.
Well, Python 2 or Python 3? No, I'm joking. Did you try any, like, is it possible with this kind of algorithms to try some Monte Carlo sampling or something? Because if you have to play like thousands of plays, I imagine you can take advantage of this kind of architectures.
Are you asking me whether you can run this as Monte Carlo?
Yeah.
Well,
or parallelizing in some way.
In the end, this is sort of a Monte Carlo. Just that, well, you're playing these games and you use random numbers as inputs. I mean, so the first distribution of the territories is random, and so the probabilities for combat are also random. So in a way, this is Monte Carlo. On the other hand, of course, it's not fully random. These are so these genetic players actually do make decisions on what to do. So, but I don't think you can take an easier approach on this than doing it this way.
Yes, we have 4 minutes left, so that's probably time for like 3-4 more questions. So one here, I saw one over here, you, yeah, that's 3 questions.
Have you considered a neural network approach for this?
No, I haven't. To be honest, I was actually, I wanted to implement a genetic algorithm once, and I thought this would be a very good problem to use it on. Neural networks, of course, usually have, well, they have other areas what they're very good at. Maybe next time I'll try another board game with a neural network, who knows.
So in the risk game, there's different phases. First, there's the initialization phase, and then there's the entire game. So you could imagine actually splitting up. So what I'm trying to say is, have you tried to find the best initialization strategy by fixing the strategy the players take in the rest of the game to see if what's the best kind of initialization you have, and the other way around, fixing the way the players initialize and then only optimizing on the second half?
I haven't looked at that. At the beginning, when I still only had the random player, I've looked at the importance of the distribution of your territories at the beginning of the game, so not the initialization, but the random distribution of the territories before that. And there I saw that this has a very large impact on the players, but of course these were random players. On the other hand, so for the genetic players, I've just used a single reinforced method to place all the armies, both in the initialization phase as in the main game. So I really cannot say anything about that.
I used to play Risk also a lot, and I remember that making deals with other players is a very important part of winning the game. Did you take account of that also?
No, so these players are very dumb. They just look at all their possibilities and take the best one, whatever that is. There is no interaction between the players whatsoever. But of course, this would be a first step. For example, if you realize that a certain player, for example, the yellow player has to eliminate the blue player, then you might want to defend the blue player to be able to, in the end, prevent the yellow player from winning and win yourself. All these things are not taken into account here. This is, in the end, just a fairly simple model.
Okay, thank you very much. Probably we will see more next year with all improved strategies, alliances, and everything. Thanks a lot for your talk. Thanks for the questions. And enjoy your lunch.